Here we are for the second video for section 4.4, and we may or may not be done with this after this one. So yes, this is a long section, but it's just there's some involved problems is all it amounts to. And so here we begin right where we left off, and that is example number 5. Example number 5, we are told that y prime equals the sine of x, and we're restricted from 0 to 2 pi, so basically 1 revolution. And we are asked to sketch the general shape of the graph. Now, realize that the first thing we're going to do is we're going to find maximum and minimum, and since we're given y prime, all we have to do is set this equal to 0 and sine of x equals 0 whenever x is equal to 0, pi, and 2 pi. And realize that we would put these on a number line to do the testing. And let's see, so I'm going to choose, well, I don't need to worry about anything over here because that's outside of our domain. I don't have to worry about anything over here. All I have to do is worry about these two intervals right here. So I'm going to choose the problem, or the value of 1 and the value of 4. Realize this is in quadrant 1, this is in quadrant 3. But it could just as easily be in quadrant 2 or 4, but it doesn't really matter because sine has the same sign each time. So whenever the sine of 1, that's in the first quadrant, so that means it would be positive, and in the third quadrant, the sign is negative. So that means this is increasing here, and this is decreasing at this point. And so we know, or then we need to look at points of inflection, or inflection points, and that's with y double prime. Y double prime is, what's the derivative of sine of x? That would be the cosine of x. And we set that equal to 0, cosine of x equals 0, so that means x would either equal pi over 2 or 3 pi over 2. Now the real problem that we have here is we have no way of determining what y is, because if we would take the antiderivative of this, this would be negative cosine of x plus c, and we really don't know what c is. So that's why we have to do just what is the general shape of it. And so that's where we're going with this. And so what I'm going to do, I should now be able to graph it pretty much. I'm only concerned between 0 and 2 pi, so I can put 2 pi out here, which means this would be pi, and this would be pi over 2, because we do have something there, and we do have something at pi over 3 pi over 2. Now one thing I forgot to do here on this number line, I need to continue the second derivative test. I'm interested in pi over 2 and 3 pi over 2. So I can choose 0, I can choose 3 here, and this would be 5, would work here. Basically, it's important to realize this is not technically the first quadrant, but that's where we can consider it. And whereas cosine in the first quadrant, it's positive. This is either the second or the third quadrant in this range. If you think about it, between pi over 2 and 3 pi over 2 is quadrants 2 and 3, and cosine is always negative in that. And then in the fourth quadrant, cosine is positive. So that means this would be concave up, concave down, and concave up. Now that we know all that, all we have to do is figure out, okay, since we're increasing here and decreasing here, that means at pi we have a maximum. So I've got a maximum at pi. I need to make sure that that is a maximum. I know I don't go beyond the 0, and I do not go beyond the 2 pi. But what I do need to realize is that at pi over 2, from 0 to pi over 2, it's concave up. So somewhere along here, it's going to turn from a concave up to, between pi over 2 and 3 pi over 2, it starts to go concave down. So between there and there, I have to make sure that it's concave down. And then from that point forward, it's concave up. And so it may have this shape, or, you know, any other numbers of shapes that we might run into. But the question is, what's the general shape? And we've done this. We have shown there's a maximum here. We did show that. and this is an inflection point as this is. We don't know exactly where it is. This could very easily be down here, but we have the general shape. It's going to take on this bell sort of shape. And so there is the answer for number 5. Don't know what happened there, but that's okay. Number 6. Number 6, we have a few pieces of information. We have, whoops, that wasn't very good. Look at your paper. This is F prime, and this is F double prime. And we need to determine which of the 4 graphs would this include. Well, if we look at F double prime from here on back, since this is positive, that means the slope is positive. So this means this has to be going increasing during this time. And likewise, from here on out this way, the slope is positive, and so it would be increasing here. Between here and here, it's actually negative slope, or in other words, it's decreasing during this time. So we know from this point, more or less, it has to be increasing. From this point going to the right, it has to be increasing, and it has to be decreasing in this middle part. Now, as far as the double prime, this is the point of inflection. We need to realize that from here to here, this has to be concave up because it is positive. And from here, since this is negative, here on back, it has to be concave down. So just in general, if we wanted the general shape, we know it's going to increase over in this direction. Oh, that's not increasing, that's decreasing. So let's try again. From here to here. It's going to be increasing here, and then all of a sudden it starts decreasing again. And then about here it starts back increasing. And we look, does this make sense? From here, from 0 on back, it's concave down, and then at some point it turns back to concave up. So this would be more or less what we might be expecting. So we just look at the choices. It has to look somewhat like that. So A can be thrown out because A looks like this. We just have what you might consider a cubic sort of look. B doesn't work because it's coming down like this, so we have to throw out B. D is in the same predicament. The only one that really looks anywhere close to this is C, and that is indeed the answer for number 6. Now 7 and 8 both require quite a bit of work, and I'm going to apologize right offhand, but understand that we're going to get this done, and we're going to look at each of the aspects, and it's going to be involved. Let's just put it that way. So let's begin with problem number 7. Number 7 is y equals x squared over the quantity x squared plus 10. So the first thing we need to do is to find the first derivative and do everything that that implies. So, well, actually the first thing we're going to do is rewrite this in user-friendly form, and we get this. At least that's the way I like to use them. Realize we could use the quotient rule, but it's going to be basically the same thing. If we do y prime in this manner, then we leave the first one alone, and we take the derivative of the second, which means take the exponent out there, take the derivative of the inside, which is 2x, and then we take whatever it was and subtract 1 from the exponent, and then we have to add that to, okay, take the derivative of the first, so that would be 2x, and leave the second one exactly alone. And let's see what that leaves us with. This gives us, okay, multiplying all that together, we get negative 2x cubed over x squared plus 10, the quantity squared. And then cleaning this up, we get 2x over x squared plus 10. Now we need to get a common denominator, which is pretty simple. It's x squared plus 10, the quantity squared. So that's going to be our common denominator. we don't have to do anything to that. But here what we need to do is we have to multiply this by x squared plus 10, which equals negative 2x cubed plus 2x cubed plus 20x over x squared plus 10, the quantity squared. So finally, cleaning this up, the x cubes cancel, so that leaves 20x over x squared plus 10, quantity squared. Now we need to determine where are the critical points. In other words, where does the numerator equal 0? Well, if 20x equals 0, then x equals 0. That's easy enough. And where does this denominator equal 0? Well, it doesn't matter how hard you try, this will always be 0 or a positive number. And when you add a positive number to a positive number, it will never equal 0. So this is the only possible maximum or minimum. So I'm just going to plug in the values negative 1 and 1, and let's see what we get back into y prime. If I plug in negative 1, I get 20 times negative 1, which is negative. This is always positive. Negative over positive is negative. Likewise, 1. Positive over positive. Numerator's positive, denominator's positive will remain positive. So that means this would be decreasing before 0 and increasing after 0. So we do actually have a maximum here. Where exactly? Well, what we have to do is we have to plug in 0 into the original. So I come back up here to the original, plug in 0. 0 squared is 0. 0 over 10 is 0. So there's going to be a maximum at 0, 0. Now we're ready for the second derivative part. So let's continue this problem. Just rewriting y prime into a user-friendly form, that would be 20x times x squared plus 10 raised to the negative 2. Once again, you could use the quotient rule, but honestly, I find the product rule a little bit easier. So that's what I'm going to be using. Now to find the second derivative, we leave the first alone. It's 20x. Take the derivative of this second one. Well, that means take the exponent, take the derivative of the inside, and leave the inside alone. Whoops. Let's try that one again. That would be x squared plus 10, and subtract 1 from the exponent to give negative 3, plus take the derivative of this, which is 20, times, leave that all alone, x squared plus 10 raised to the negative second power. Now just clean this up. 20x times negative 2 times 2x would be negative 80x squared over x squared plus 10 raised to the third power, plus 20 over x squared plus 10 raised to the second power. And we need to get a common denominator, and much like in the first derivative, the common denominator is pretty simple. That is x squared plus 10 quantity cubed. And we don't have to do anything here, so it's negative 80x squared plus, and all we have to do to this one is multiply by x squared plus 10. So it's just a matter of cleaning it up. X squared plus 10 quantity cubed down here at the bottom, and this becomes negative 80x squared plus 20x squared plus 200. And finally, combining the like terms, this is what we get. Negative 60x squared plus 200. Now once again, we need to set both the numerator and the denominator equal to 0. The denominator, once again, still will not ever become 0, so we don't need to worry about that. Instead, all we have to worry about is what is negative 60x squared plus 200 equal to 0. So negative 60x squared would equal negative 200. X squared would equal, what, 5 halves, I believe. Is that right? 20 over 6 would be 10 over 3. Oh, 10 thirds, not 5 halves. have no idea where that came from. Oh well. Easily enough fixed. And so x would equal the positive or the negative square root of 10/3. So now we have to come over here and do negative square root of 10/3 and positive square root of 10/3 and try some values. Well, I'm going to choose the value of 0 here. Let's see. This would be 2 as a legitimate value and negative 2 as a legitimate answer there. And so if I plug in 0 into y double prime, which is right here, plug in 0, this becomes 200 in the numerator, and this basically this becomes positive here, and this is always positive. The denominator is always positive in this particular problem, and so positive over positive is positive. Plugging in negative 2, we get negative 60 times 4, which is negative 240. Negative 240 plus 200 is negative 40. Negative over positive is negative. And the same thing is going to apply with positive 2. It doesn't take too much to realize this final answer will be negative. So we now have the fact that there is a point of inflection at each of these places, because this says, or this tells us, that this is concave downward, concave up, and concave down. And so now what we need to do is we need to find out what are those values. So, and we plug this into the original, the y, not the y prime or the y double prime. And so if we plug in the square root of 10/3, after we plug it in, I'm not going to spend the time going through it, we end up with 1/4, positive 1/4. And when we plug in the positive square root of 10/3, we end up with positive 1/4. And these are points of inflection. We know that it's going to be concave down before this, concave up between them, and then concave down after the positive one. So let's see what all we have here. We have the point 0, 0. That's easy enough to find. Square root of 10/3, 1/4, maybe somewhere out here. And negative square root of 10/3, 1/4 would be just reflected through the y-axis. Now we know between here and here, the two inflection points is concave down, so I know this has to go something like this. Or I'm sorry, it has to be concave up. It has to be scooping up. So there, we've got it going up. But everything going off into the left, I know it has to be concave down, and likewise way over here to the right has to be concave down. And these can't be maximum because they did not show up in our first derivative test. So that means we just have to make sure that it starts curving back this way, that way, and we have to make sure that it starts curving back this way. And basically it's going to go forever in a concave downward sort of position. So this is roughly what the sketch is going to look like. It's concave down, 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 then all of a sudden it's concave up, then it's concave down. And the only extreme value is right here at 0, 0. I have no idea what's going on with those, but oh well. Okay, now we're going to 8. 8 is a lot of fun as well. And so let's see what we've got here. Number 8, we start off with y equals 6x over x squared plus 9. And we need to go through the whole process, the first derivative test, the second derivative test, so on and so forth. So we begin with the rewriting this in user-friendly form. So that'd be 6x times x squared plus 9 raised to the negative first power. So y prime will be leave the first one alone, take the derivative of the second, which means the exponent, the derivative of the inside, and leave the inside alone, changing the exponent. So that's what we get. Plus, okay, take the derivative of 6x, which is 6, and leave the second one all alone. Rewriting it into a more acceptable form, and actually something we're going to have to deal with. We know x squared plus 9 quantity squared goes down here in the denominator, and up here would be negative 12x squared. Plus, this one would become a 6 over x squared plus 9. Well, to get the common denominator, all we have to do is multiply this by x squared plus 9 over x squared plus 9. So our common denominator is x squared plus 9 squared. So this would be negative 12x squared plus 6 times x squared plus 9. And now it's just algebra to straighten this up, or to clean it up. X squared plus 9 quantity squared down here, and this is negative 12x squared plus 6x squared plus 54. We can combine these two because they are like terms, and so this becomes negative 6x squared plus 54 over x squared plus 9, the quantity squared. Okay, x squared plus 9 is always positive. It will never be, and besides when you square it, it will always be positive. So when we do the plugging in, it will be relatively simple. At the same time, this denominator will never equal 0, so there's no critical point at that point. Instead, all we have to do is say, okay, negative 6x squared plus 54. What's the answer here? Subtract 54 from both sides, and divide both sides by negative 6 so that x squared equals 9. Therefore, x would equal plus or minus 3. So those are the potential minimum and maximum at negative 3 and 3. So I'm going to choose 0, negative 4, and positive 4. I'm going to do the easy one first. Plug in 0 into y prime, which is right here. Well, I know the denominator is positive, so it doesn't really matter. I'm always going to be positive there. What matters is up here. Plugging in 0, I get 0 plus 54, positive. So positive over positive is positive. If I plug in 4, negative 6 times 16 is negative, 96? Negative 96 plus 54 is negative. And negative 4 is going to give you the exact same value because all that happens is this squares and it ends up being exactly the same. So this is negative. So this means this is decreasing, this is increasing, and this is decreasing. Now, where exactly? Well, let's get those points taken care of right now at negative 3 and 3, plugging those into the original. So we plug in negative 3, we get negative 18 over 18, which is negative 1. Plugging in 3, we get a positive 18 over 18, which is a positive 1. So we need the point negative 3, negative 1, and 3, 1. That is where we are dealing with the maximum minimum. And we look, if it's decreasing and then increasing, this better be a minimum, and this would be a maximum. Now let's see what happens when we take the second derivative. But in order to do that, let's first off, the y prime, let's change that. I recall it's negative, oh no, I've got wrong notes again, so I need to come back up here and see what it is real quick. Y prime is negative 6x squared plus 54. Okay, so I'm going to rewrite it in user-friendly form, so it would be negative 6x squared plus 54 times x squared plus 9 raised to the negative 2 power. So that's my y prime in user-friendly form. So let's see how we would find y double prime. Y double prime equals, leave the first alone, negative 6x squared plus 54. And take the derivative of this, which means the exponent, the derivative of the inside, and leave the inside alone, but just affect the exponent. plus, take the derivative of this, which would be negative 12x times, leave all the rest alone. So clean this up, and here's where it doesn't come in so nice. We have x squared plus 9, the quantity cubed. And let's see, how does this all change? Okay, this will be negative 4x if I multiply those together, and I'm going to go ahead and distribute to this. So negative 4x times this would be 24x cubed minus, let's see, that would be 216x plus, cleaning this up, negative 12x times x squared plus 9 quantity squared. But you know what, let's kill two birds with one stone here and realize that it's easy to see that the common denominator is this, so all I have to do is take the negative 12x and multiply by another factor of x squared plus 9. And so this will all equal, going to do two steps here, save a little bit of time and some space, because I'm going to have to pause it just temporarily. I'm going to go ahead and distribute over here and combine any like terms. So I look at it and I've got 24x cubed here. This is going to be negative 12x cubed. 24x cubed minus 12x cubed is 12x cubed. And then this becomes negative 108x when I take negative 12x times the 9. So negative 108x, and I had negative 216x, so that would be negative 324x. And so this is y double prime. So once again, we have to figure out, where does it equal 0? The denominator will never equal 0. And perhaps even more importantly, it will always be positive, because we'll have a positive plus a positive, which is positive. Positive cubed is positive. So it's never going to be negative even, to help us when we actually plug in the values. But we have to figure out, where is this going to actually equal 0? And so this is what we do. We set 12x cubed minus 324x, set that equal to 0. I can factor out, let's see, does 12 go into 324? Be 284. Yes, it does. So I can pull out a 12x, leaving x squared minus 284 would be 7. And so 12x has to equal 0, or in other words, x equals 0, or x squared minus 27 equals 0. And so x squared would equal 27, which means x would equal plus or minus 3 root 3. Just a fairly quick simplification there. And so now I'm going to look at the value of 0, negative 3 root 3, and positive 3 root 3. And so let's see what values work here. Negative 1 will work here, positive 1 will work here, and let's see, 6 will certainly work here, and negative 6 will work here. So we have several different values we need to try, and this is going to go back into y double prime, which is up here. So plug in negative 1, we get negative 12 plus 324. Well, that's obviously positive. The denominator will always be positive, and so positive over positive ends up being positive. Plugging in 1, we get 12 times 1 minus 324 times 1, the big or huge negative number here. Negative over positive is negative. Plugging in negative 6, and here's where it's not quite as simple, but realize that if you plug in negative 6 and cube it, you get a pretty big negative number, but you get a pretty big positive number here. But as it turns out, that will be negative, and likewise here at positive 6 we end up with a positive, which means, since this is the second derivative test, this is concave down, concave up, concave down, concave up. So at these points, at 0, let's see, I have to plug in 0 into the original, so that would be 0. and I have to plug in negative 3 root 3 and positive 3 root 3 into the original. If I plug in negative 3 root 3, what I am going to do here is to come up with some approximations. Really, if I don't worry so much about the vertical scale, I'm going to be able to get a fairly decent graph. But let me pause for just a second, and so I can get my calculator. Okay, I am back with a calculator in hand, and so if I actually calculate, okay, what is 6 times negative root 3, or 3 root 3, divided by the whole quantity, negative 3 root 3 squared plus 9, we get, well, be negative 18 negative 18 over 36. Oh, that's not right. Negative 18 root 3 over 36, which is negative root 3 over 2. Okay, so let me do that. Negative root 3 over 2. And if we plug in the positive, then the only difference is we're changing the sign from negative to positive. So we get these values right here. So now we have all of our points that we could possibly need. Let's go back up and review. We have a minimum occurring at negative 3, negative 1. We have a maximum occurring at 3, 1. So I need to put those in. And these values here are inflection points. So negative 3, negative 1, be about right here. 3, 1, be about right here. We have an inflection point at 0, 0. Let me change this just a little bit. At 0, 0, we have an inflection point, and we know that it's going to go from up to down, so it's going to go like that part in right there. And then we also know at negative 3 root 3, which is about right here, negative 3 root 3 root 3 over negative root 3 over 2, which is about right there. So this is negative 3 root 3 negative root 3 over 2. And corresponding value would be about right here, which is 3 root 3 root 3 over 2. And we know it's at those points where it now becomes concave up again. So, combining everything, we know this is a maximum, this is a minimum, and it is concave down from here to here. So I need to slowly bring it over there, and then it's concave up everywhere else. But this still has to be a maximum. So we need to think about how can we do that. So let's see what we can get here. Okay, this has to be concave down here. It has has to be concave up. How can that be a minimum or a maximum and it still be concave up elsewhere? I'm going to continue with this and just we'll eventually get this worked out. I'm going to have to do some recalculating, but it basically is going to look something like that. We've got this nice little curve sort of thing going on here in the middle, and then it goes up and down on either side like this. This is the shape that it should take on. It's just there's something that's not quite right. I will try to point that out at a later point. But unfortunately, we weren't able to finish them all, so I need to go to another video that will get the last three examples. The last three examples are quite simpler and not near as much time as the others. So here we go.